Thank you very much for having me. It's a pleasure to be here. So I'm going to be talking about a very recent paper, the title Spread of Misinformation Over Social Networks. It's joint work with Daruna Semoglu from Department of Economics and Ali Farendegebi from Department of Electrical Engineering and Computer Science. I am also in Department of Electrical Engineering and Computer Science. So it's not a paper in mechanism design, but it relates very strongly to the notions of robustness, stability of dynamics, how do we aggregate behavior, or how do we come up with macroscopic outcomes from individual interactions. So hopefully it will be of interest to you. So essentially we're interested in belief formation in social networks. And the setup is as follows. So individuals have beliefs about certain economic, political, social issues, which we generically refer to as an underlying state of the world, based in part from the information they get from their friends, neighbors, colleagues, as well as local news sources or some local leaders. So this belief will be an accurate estimate of the underlying state if individuals have dispersed, unbiased information, and there's some efficient information aggregation mechanism. For instance, if the individuals have conditionally independent signals about the underlying state, and they observe a lot of their neighbors, large number of neighbors, then a law of large numbers type of argument ensures that they learn the true state. However, in practice, misguided, biased views are ubiquitous, and the individuals are often swayed by misleading ads and political campaigns and so on. So examples are abundant, but I just wanted to pick a couple. For instance, if we look at the SwiftBoat ads during the SwiftBoat ads have been very influential on the independent voters during the 2004 presidential elections. A large fraction of population in the Middle East believes that 9/11 was a U.S. conspiracy. This includes also 28% of U.S. Muslims. And as of 2007, 41% of the U.S. population still believes that Saddam Hussein was directly involved in 9/11. So, motivated by these examples, the question that we would like to ask is, can we understand how this type of misinformation spreads in societies? And in particular, can we quantify the extent to which beliefs are affected by opinions of these forceful individuals that are wishing to influence others? In particular, we're basically interested in providing some insight into what type of societies or communication structures are robust to misinformation. So to investigate this question, we model the society as a collection of agents who are connected to each other through a social network and also communicate and exchange information with not everybody, but just a sparse neighborhood of individuals. So learning here I'm going to be using quite a lot. So by learning I mean forming correct beliefs about the underlying state. And I'll be more precise about this in a second. So since we focus on spread of misinformation, we will adopt a non-Bayesian framework. Just a quick sort of comment about why not Bayesian learning. Well, with Bayesian learning, the model that we have to consider will be different. The influence on the views of an agent will depend also on his belief about the person communicating with him, whether he's trying to influence him or not. So those type of inferences that we need to form will make the analysis complicated and also limit the extent of misinformation. So our use of non-Bayesian framework here is really a worst case type assumption. What's the worst case that can happen in a non-Bayesian setup? And also, if you want,
you don't allow to learn bad things. So learning.
No, we're not. We're not adapting the rule. We're essentially going to adopt the rule of thumb type learning dynamics and analyze that. So with Bayesian learning, we know some things from our earlier work. Basically, a finite number of influential agents would have no impact on the asymptotic beliefs. This is our recent paper from OH. Essentially, it's a model of Bayesian learning over an arbitrary social network. Essentially, here the belief or posteriors are generated in a Bayesian manner, and in an adaptive manner. And the main result here is when individuals have unbounded beliefs, meaning unbounded likelihood ratios, and also if they are under some weak regularity conditions on the structure of the network, asymptotic learning will obtain. And the immediate corollary of this will be asymptotic learning will not be disrupted by a finite number of agents having misinformation. Essentially, individuals will recognize those forceful agents and downplay or accordingly adjust the weights that they give to their information or their action. So,
but it might take a very long time.
True. True. We don't know. We're not claiming anything about rate. This is an asymptotic result. But given that in this kind of setup, we don't have we cannot characterize the extent, we would like to look at a non-Bayesian formulation. So that brings us to the model of this paper. So we focus on non-Bayesian or rule of thumb learning. And we assume that the society consists of two kinds of agents: regular agents who wish to exchange information, and forceful agents, which are opinionated individuals who wish to influence the opinions of others. So here is our interaction structure. We assume that agents are matched according to an arbitrary communication matrix P, which captures the underlying links, communication or social links that are present. So essentially, that's the representation of the underlying network. So with some random probability Pij, agent I observes J, and they meet. And as a result of this meeting, we're going to assume that there will be some exchange of information which affects one or both of the beliefs of these agents. So we assume two kinds of scenarios. So I is meeting J. If J is a regular agent, we assume that meeting essentially is an exchange of information. So they agree with a pairwise specific probability. And when they agree, we assume that they update their beliefs to be the average of their original beliefs. In the second case, if J is a forceful agent, again with a pairwise specific probability, we assume that agent I is influenced or convinced by agent J, in which case J's opinion remains the same. He's a forceful agent, but I essentially inherits most of the opinion of the other agent. Okay? So
the matrix P is symmetric then?
No, not necessarily.
So it's not like they're meeting, it's just it's observing.
It's observing. I meets, that's the way I'm using it. Essentially, I is observing J, and Pij need not be equal to Pji. Okay? So, So essentially, the question, this is the type of interaction structure that we would like to analyze and understand what the limiting distribution looks like. So how do we analyze this? So this is essentially a stochastic dynamics and relates to some of the questions from yesterday. So stochastic approximation could be one methodology to analyze this. But actually, this is this has a little nicer, more tractable structure. In particular, we can write the evolution of beliefs as a linear stochastic time-varying update rule. And once we have that update rule, essentially we can analyze it by relating it to the transitions of a time non-homogeneous Markov chain. So we're going to do that. Essentially, we're going to write down the belief evolution related to this Markov chain. Then we can do the convergence analysis using a Lyapunov function argument. In particular, we're going to show that these beliefs will converge to a random variable, a stochastic consensus value. Then the question becomes, okay, these agents reach a consensus, but how can we measure the social influence, the extent of the influence of these strong agents in this arbitrary network? Our measure of social influence will be how far is the expected value of the stochastic consensus from the average opinion of the society. And to do that, essentially what we're going to do is we're going to consider this Markov chain, the mean transition matrix of the Markov chain. We're going to decompose it into two parts, the doubly stochastic parts and that sort of the symmetric part, as well as the influence matrix, the non-symmetric part. The symmetric part is one which essentially averages opinions. So essentially the way we're going to analyze it is we're going to try to understand the stationary distribution of this Markov chain, and we view this influence matrix as a perturbation on the original Markov chain. So essentially we're going to develop bounds on the behavior of the stationary distribution using perturbation theory from Markov chains, some beautiful results of Schweitzer. We're going to use spectral graph theory to relate the effect of influence or effect of the underlying network structure on the total influence. And we're going to essentially also extend or improve upon our results using some results from linear network optimization min-cut max flow theorem. So just to summarize our results, again, the notion of learning will be almost sure convergence to consensus with 1/n weight on the initial beliefs of each agent. So the reason we're using this as the notion of learning is essentially it's capturing aggregation of decentralized information across agents. So that's basically, we are interested in whether or not agents will converge to 1/n average of their initial beliefs. So in the absence of forceful agents, it's actually not too hard to show that the beliefs converge to 1 over n weighted average almost surely. So our first result says even in the presence of these forceful agents that exerts influence on others, beliefs still converge to a consensus almost surely, but this is now a random variable. So the next question is how far is this random consensus from the 1 over n weighted average? We'll make a key assumption, which we can discuss. This makes a big difference in terms of our result. Essentially, I'm going to assume that even forceful agents obtain their information from others. So I'm thinking about a connected, strongly connected network.
I was just going to ask if this Markov chain, if it has a unique invariant distribution, and if you've ruled out aperiodicity.
That's how I will rule out aperiodicity. But even without that assumption, I think I can show convergence, but the results will be different. The bounds will be different. So this is a key assumption in the bounds.
You get convergence of the time averages, I guess, but you think even without that you can.
It may not be unique, but I think there may be. That's the assumption under which I'm going to show. In the other case, we can also do other things, I think. But this is a key assumption that I think is important to keep in mind. We're assuming a connected society, that even the forceful agents get their information from other agents in the society. So the second set of results are essentially bounds on the gap between this mean consensus and the 1 over n weighted average as a function of the size of the society. And we're going to show that as n, the size of the society gets large, holding the number of forceful agents constant, consensus will be arbitrarily close to 1 over weighted average in some topologies. I'm going to show you what kind of topologies are those. Essentially, our bounds will be a function of the number and the connections of the forceful agents. And here, the network topology. And the property of network topology that becomes relevant in these bounds is whether or not the induced Markov chain is slow mixing or fast mixing. So the convergence rate properties of the underlying Markov chain will dictate how big these bounds are. So the second set of results improves upon these. Essentially, these are general bounds, upper bounds, but we're going to also provide exact characterization of this difference in terms of the mean passage times of the induced Markov chain. So that's really abstract, doesn't tell us much about how it relates to the underlying graph properties, but motivated by mean passage time, we're going to show that actually the real relevant property of the graph is these minimum cuts between regular and forceful agents, essentially number of edges between subsets of nodes that include the influential and the regular agents in the graph. So those are I'm going to talk about these in more detail. Related literature. So there's a large literature on learning, both on Bayesian and non-Bayesian. I'm just going to cite those which are relevant to our update rule and has similarities with our dynamics. Essentially, the most relevant are the papers by De Groot, Demarzo, Vajanos, Wiebel, and mainly the recent papers of Golub and Jackson from 07 and 08. So here, basically, these two papers are also interested in learning models over social networks represented by connected graphs. So for the belief update rule, they use simple averaging rules motivated by De Groot. Instead of the pairwise interaction that I was talking about, random pairwise interaction, they just assume that every agent takes an average, similar to the dynamics that Simon was talking about, takes an average with the beliefs or opinions of the neighbors around it. And essentially what they're interested in is providing conditions on the network structure. First of all, they derive, again, similar consensus type results. And then they're interested in conditions on the network structure that under which those limiting consensus beliefs are equal to the 1 over n weighted averages. So type of conditions here are something similar to doubly stochasticity. So they think about expanding graphs and getting doubly stochasticity in the limits, which is sort of nice, but also restrictive in view of the fact that we don't really have the symmetry of balancedness condition in many of the social networks. So there are some hubs or there are some nodes which are actually have higher degrees than the rest of the nodes in the graph. So essentially what we're doing here is, instead of looking at conditions under which we can get the 1 over n average, we're providing an alternative model of spread of misinformation, which turns out to be more tractable to characterize and quantify the impact of these influential agents. So let me sort of define the model a little more formally. So we're thinking about a finite society consisting of a set n of agents. So we have n agents. Each agent is endowed with an initial belief xi of 0, which is a belief about the underlying state. So we're interested in whether or not social beliefs or consensus reflect the initial average, mu, which is 1 over n xi of 0. And essentially the idea here is that an extreme xi of 0, if we can get, or if we can learn this value, an extreme xi of 0 will have little influence on mu, because 1 over n will be small. However, if we have forceful agents, and forceful agents are those whose initial values get a weight which is different than 1 over n, so then, those may have a large impact on the consensus belief. So that weight that their initial belief gets measures the extent of the social influence.
Is the xi a vector or
X,
is it a real number?
in the paper, we assume a real number. Nothing changes in the analysis if we assume vector values as well. So as long as each component is updated with the same interaction structure. So let me actually show the dynamics, and maybe we can talk about that in a second. So the model for communication and information exchange is as follows. We assume that time is continuous. Each agent is recognized according to an IID Poisson process. So this implies that the communication instances happen according to a Poisson process, and let's say at times tk. And each of these communication instances tk, each agent has an equal probability of being recognized. So now, given the TKs, I discretize time according to these communication instances, because those are the only times relevant for us in terms of belief updates. So I index that by K, 1, 2, 3, 4. They index states of communication. I basically use xi of K to denote the belief of agent I after the kth communication. So conditional on being recognized, agent I observes agent J with probability Pij. Conditional on I observing agent J, 3 things can happen. So with some probability beta ij, the two agents agree and exchange information, in which case both update their beliefs to be the average of their previous beliefs. With probability gamma ij, there is disagreement, there is no exchange of information, everybody sticks with their previous beliefs. And with probability alpha ij, I is influenced by j. And in this case, I assume that I adopts a large portion of J's belief and only puts epsilon weight to his original belief. We can, so this epsilon positive helps in the convergence analysis a little bit, but it's really a technical assumption. We can also assume that epsilon is equal to 0. So we say that J is a forceful agent if this probability of influencing I is positive. Okay?
Could you go back to the previous slide for just a second? Okay. So there you define forceful agents as having extreme beliefs, but on the next slide you define them as having positive.
Positive, yeah. So
is it both?
It's not very precise. I mean, I wanted to motivate forceful agents by saying they may have potential beliefs. This is the mathematical definition I'm going to use.
But they might not actually have.
They may not.
Okay.
They may not.
Okay.
I was just trying to motivate to say, why we're actually thinking about forceful agents essentially having a different weight. But this is the more mathematical definition. Sorry about that. Okay, so this is the interaction structure. So how do we sort of analyze this kind of dynamics? So I'm going to aggregate all of those beliefs at time k into a vector. And I'm going to assume that agent beliefs are updated according to this dynamics. Now, going back to your question, I could also think about these being vectors, and each component of the vector being updated by the same W of K matrix. All of the results also extend to that case. So essentially, we're thinking about the underlying interaction affecting all the components of your belief vector in the same manner. Yeah. So WK here is a random matrix given by, now if you remember, Pij over n was the probability with which I communicates with J. Beta ij was the probability with which they average. So we can write it compactly in a matrix form as this. So I'm going to refer to that matrix as an Aij. So Wk is equal to Aij with this probability, equal to the influence structure with this probability, and nothing happens with the rest of the probability, gamma ij. So if you look at this matrix Wk, it's a random matrix, and also it's a stochastic matrix. In the sense, all the rows of this matrix add up to 1. And moreover, it's independent and identical because we have this IID assumptions at each point in time. It's also an IID matrix. So essentially, we're looking at this dynamics and asking the question, how do we analyze this? So because of the stochasticity assumption, it goes back to the Perron-Frobenius theory, but the only difference now is that we're thinking about time-varying matrices here. But it's really an extension of the same idea. What we do is we introduce, so essentially I want to be able to write the beliefs at time k as a function of beliefs at an earlier time s or time 0. So to be able to do that, I multiply these. Because of the linearity, even if it's time varying, I just have these transition matrices that I can use to relate the beliefs at time k to the beliefs at time s. Yes?
Why is W written as a function of K? It doesn't seem to depend on K.
But at each point in time, essentially, it takes different forms with some probability.
It's drawn from a distribution.
Yeah, well,
So it's
the
a different-
distribution's the same every period.
Yeah,
This
so
is the same, but this is a realization.
this is a realization. So
It's just a notation thing, I understand.
you're right, especially if I look at the mean behavior of this dynamics, k drops out. But for now, I want to keep the k to just tell you that the realization at each point in time may be different. So, okay, so we have this kind of dynamics that we would like to analyze. So to be able to understand the convergence behavior of this, all we need to understand is how these matrices, the products of these row stochastic matrices, behave. So before I get to it, and that these will ensure some of the assumptions that you were talking about, irreducibility, aperiodicity, I make some assumptions on our model. The first one is about communication probabilities. This one is, I think, very natural. First of all, I assume PII are all equal to 0. Nobody communicates with himself. So PIs are indeed probabilities. These are essentially non-negative for all ij, sums to, for all I, it sums over j to 1. So it's a natural assumption. And let's also recall our notation. P is our communication matrix Pij, not necessarily symmetric, but row stochastic. So I look at the mean connectivity graph, and this is basically the set of agents that we had before, right? This is our set of agents, n of them. And I assume that there is an edge, so I put the edges in the graph such that, so it's a directed graph, so I put an edge between I and j if Pij is positive. So essentially this kind of model captures any kind of graph that we can think about. So the connectivity assumption I make is on this mean connectivity graph. I assume that NE is connected, so actually it's strongly connected, between every pair. It's a directed graph, so I need the strongly connected notion in the sense between any I and j. If I pick any nodes, there's a path that connects I to j. And this is essentially, because I'm looking at the probabilities, it's essentially a connectivity assumption on the expected communication graph of these interactions.
It's just saying the matrix is irreducible. That's what it is.
That's what it will come to, together with the beta. I'll come in one more assumption, and that's what it will amount to. So the final assumption is on these interaction probabilities, because even if the P's, the corresponding Markov chain to here is irreducible, I have also this beta and alpha parameters on top of it. Together with the P's, I need the entire thing to be reducible. So what I assume is for all ij in E, this sum is positive, beta ij plus alpha ij. So what does this mean? This means that for every agent, either they average over all these edges in the graph, beta ij will be positive or alpha ij will be positive. So meaning that there is no agent that influences everybody, but doesn't get any information from anybody else. So we are ruling out that scenario. So even like if we have a CNN, even CNN gets information from his reporters. So whether or not that's a good assumption, we can, I think it's a very interesting thing to look at this first and then also look at the case when that's not the case. So otherwise, I will just, it's not a connected network. Sorry.
Well, is there a reason why? So the previous assumption was that any I and j are indirectly connected by some path, right? With positive PIJs. Would it be enough to just assume that the beta plus alphas were positive along that path rather than doing it for all IJs?
It has to be true for all such paths. So if I have to look at all pairwise nodes, all paths between, because essentially I need any pairs, I need to make sure that information propagates from one to the other.
So in the previous, though, you're saying there's at least one path from I to J.
Yes.
And it seems like if the beta plus alpha terms were positive along that one path, then there would be transition.
So the most tight condition is look at every pairs of nodes, look at one possible path between those, and make sure this holds.
Yeah, okay.
I mean, yes.
I didn't understand if the agent A always observes agent J. You know, if it is a probability to observe another agent, or if the observing agent always observes the same set of agents.
No, not necessarily.
Not necessarily.
So we can.
It connects each time with a random agent.
Yeah, we can have all these three different neighbors, and with some probability you observe this one, with some probability you observe this one, and there's some pairwise specific probabilities which dictates the social interactions that happen. Okay, so those are the assumptions, and now the preliminary result, I'm calling this a preliminary result because without the influence matrix, if we have the rest of the interactions, averaging, nothing changing, that's pretty, it's a folk theorem, I would say, that actually under the assumptions that I talked about, if there are no forceful agents, alpha ij equal to 0, then the beliefs xik converge to a consensus with probability 1. So this is essentially, I'll use it as a benchmark for comparison. So if there are no forceful agents, if all the interaction, because we're doing, even if the underlying P is not symmetric, we're picking two agents at each point in time and they're averaging. So everything really is symmetric. So it's expected that in time we will be able to average the opinions. So what happens when there are these forceful agents, namely the effects of these alpha ij's positive? So under the assumptions that I talked about, the beliefs xik converge to a consensus belief x bar, so some scalar random variable with probability 1. So the difference is that now we're no longer converging to a point, but a random variable. Rate of convergence can be written here as a function of the spectral properties of the underlying mean connectivity graph. I didn't do so because it's pretty bad, especially in view of the fact that if we had doubly stochasticity in the interaction matrix, things are pretty fast. I mean, I'm not sure. When we have this kind of symmetry in this graph, the underlying Markov chain mixes quickly, fairly quickly. But when we lose the doubly stochasticity, the convergence rate can be very slow. It's basically exponential in the number of nodes in the system. So let me quickly go over the proof sketch to give some idea about how we can prove such a result in the case of this time-varying dynamics. Essentially, I look at this transition matrix, phi. So I'm getting the product of these matrices from some arbitrary time s to s plus n squared d minus 1, where d is the maximum shortest path length over any ij in the mean connectivity graph. So what I can show is basically, if you look at that graph, that matrix, that transition matrix, all components of that matrix is bounded away from 0. So we can write down the uniform bound on the components of that matrix. So why is that an important property? If we go back to a simpler case where we have fixed matrix multiplying this dynamics, what this is saying is essentially that matrix is a primitive matrix. So essentially, it is ergodic, it has a stationary distribution. Moreover, this is a stochastic matrix we're talking about. The sums are equal to 1. So if it's a primitive matrix, we know that it has a largest eigenvalue. All the rest of the eigenvalues are strictly smaller. If it's a stochastic matrix, we know that that largest eigenvalue is equal to 1. So the second largest eigenvalue is strictly less than 1. So that's what allows us to get convergence. And essentially, that's the same idea extended to this case. So this is some sort of primitive matrix type property.
Strictly less than 1 in modulus.
Yes. So strictly less than 1 in modulus, exactly. So once we establish this, we need to pick an appropriate Lyapunov function to get improvement over these paths and then get convergence. So here the natural Lyapunov function one can take is the maximum and the minimum between the beliefs of these agents. So we expect that to converge to 0 in the limit. So I look at this different individual beliefs of the agents. I take the maximum, minimum, and I show that that strictly decreases with positive probability, which allows me to get with probability 1 convergence in the limit. So that's the first result. And the second one is basically about how do we characterize. Now that we have established xik's converge to some x bar over any arbitrary graph, how do we actually provide an upper bound on this difference? And I'm looking at the expected value here. That's my measure of social influence. So to do that, basically, I look at this WK. Now take the expected value. Because of the ID assumption, we have no dependence on time k. So W tilde is our mean interaction matrix. So it can be viewed as it's a row stochastic matrix, sums to 1. So it can be viewed as the transition matrix of an irreducible aperiodic Markov chain. Irreducibility comes from the connectivity assumptions. Aperiodicity comes from the I think that's right. Because we have positive diagonals, we have these self loops, which essentially gets us the aperiodicity. So under those conditions, it's well known from Markov chain theory, there is a limit vector probability stationary distribution here, and moreover, the expected value of x bar can be written as the convex combination of the initial beliefs, but no longer with the 1 over n weights, no longer with the uniform distribution, but this sort of convex combination coming from the stationary distribution of this Markov chain. So really, to be able to understand these weights that I was talking about, so whether or not an agent gets a weight which is larger than 1 over n, we need to characterize this stationary distribution, which is not an easy task. But essentially, the trick we're going to use here is this perturbation theory. So we're going to provide bounds on how far this expected x bar or the stationary distribution is from the uniform distribution. And the first set of bounds will depend on two things. The total influence, which is basically Pij, probability of communication, alpha ij, probability of influence, and 1 over n is coming from this asynchronous communication model, as well as a parameter delta. So this parameter I'm going to talk about in a second, but it essentially relates to the mixing time of the graph. What's the mixing time of the graph? Well, it's the convergence rate of the corresponding Markov chain to the stationary distribution. So that's a very interesting intuition or result. It's not immediately obvious why the mixing properties or convergence rate properties relate to these bounds here. But the intuition, the economic intuition, I think, is as follows. So basically, mixing properties matters because in a fast mixing graph, the opinions of the community influence these forceful agents before the forceful agent can infect others. So, and because of the connectivity assumption, they can do that. So essentially, that's what allows us in a fast mixing graph to get bounds which are smaller. Essentially, the impact of this influence on such graphs is limited. And I will give two theorems. The first one is basically this, which relates it again in terms of the difference to the total influence as well as delta. Here, delta is a parameter. I'm just going to say that it relates to the maximum shortest path length in the mean connectivity graph, as well as some of the other parameters. It's the network properties. It's a crude bound. It comes from the Lyapunov analysis I have showed before. Let me just quickly show how we prove this result. We pick a beautiful result from this perturbation theory of Markov chains. It's a thesis, actually, from MIT math department, 68. I was very happy to find it when I found it in the library. So essentially what it says is it allows us to characterize stationary distributions. So we're looking at an irreducible aperiodic Markov chain with transition probability matrix T and stationary distribution pi. Now, we look at the fundamental matrix of that Markov chain defined as follows. It's the inverse of, this is the identity matrix minus the transition probability matrix minus the matrix of stationary distributions. Now, it's straightforward to show that we can write Z this way. So it's essentially an indication of, or a sum of, T to the K is K step transition probabilities. So how quickly we are getting to the stationary distribution sound. And similarly, related to the fundamental matrix, we also define the deviation matrix as fundamental matrix minus the limiting distribution matrix. So Schweitzer's result says the following. If you have this Markov chain T, and if you perturb it with some other matrix D, and the D is a matrix such that each row sums to 0. So when you add it, essentially it keeps the Markovian property of the original chain. So essentially we're looking at this perturbed Markov chain T hat. Assume it's also irreducible and aperiodic. So then the perturbed Markov chain has a unique stationary distribution pi hat, and moreover the change in the stationary distribution, which is D, or pi hat minus pi, can be written exactly in terms of the deviation or the fundamental matrix of the Markov chain, of the original Markov chain, as well as the perturbation. So we're going to now take this result and sort of see what that means in our setup. Essentially, this is the belief update rule. I take the mean interaction matrix. It's an expected value. So I decompose it into two parts. I move the symmetric part, which is the averaging part plus nothing happening part, plus the influence part. Now this influence part is really our perturbation. So now I put a bound on this infinity matrix norm of dy. So dy is using the representation from before, t to the k minus t infinity. Now t infinity in our case is the uniform distribution. If you multiply it with a deviation matrix, which all the rows sum to 0, dt infinity is 0, so all we are left with is dt to the k. So now I take dt to the k and then use again the similar Lyapunov function, max minus min, to be able to write down what that bound is on the matrix norm, which gives me this d infinity. So essentially I make use of this Lyapunov function and how fast it decreases to be able to write down an expression in terms of the network properties on the bound. So that's one expression using this Lyapunov function. One can write, so that was an infinite norm. Now I'm looking at the 2 norm. I can pick up another Lyapunov function. And my goal now is to actually see basically what are the network properties. Can we understand, other than this length of these paths? Is that really the property that affects these bounds? So first order of business that we tried was, actually let's use another Lyapunov function, and we were able to relate the bound, this is a tighter bound than the previous, to lambda 2, where lambda 2 is the second, again, modulus, largest eigenvalue of the matrix T. Here T is the doubly stochastic part of the mean interaction matrix. So lambda 2 is related to the mixing time of a Markov chain, and 1 minus lambda 2 is the spectral gap. So what this result is saying is, when the spectral gap is large, namely lambda 2 is small, or the graph is fast mixing, then essentially the implication is that okay, if the Pij's, this sum term is small, okay, let me go step by step. So if the sum term is small, then the perturbation is small, or the deviation is small. So that says that if, for instance, just quickly, if this term is small, we're close to the mean here. Moreover, if the Markov chain induced by T is fast mixing, again, misinformation will not spread in that network. So now I'm going to basically use some more powerful tools to understand how I can relate lambda 2 to the network properties, because that's really the key objective here. Some macroscopic properties of the very complicated network that tells me these kinds of networks are robust against spread of misinformation. So to do that, so we have a bound in terms of spectral gap. To relate it to network properties, I use the notion of a conductance of a graph. So what is the conductance? So I take this transition probability matrix T, and different from this Pij, which was a directed graph, this T is now symmetric. So with that symmetric T, I associate an undirected graph. So the edge node set is 1 to n, and edge weights are this Tij. And if you go back to the model, it's essentially Pij plus Pji. So it becomes a symmetric matrix. So the conductance of the graph is defined as follows. Look at subsets. So partition the graph into 2, and look at the cut between the 2 partitions. Add the weights over over this cut, and then normalize it with the cardinality of the smaller set, namely the set that contains less than n over 2 of the nodes. And that's the notion of conductance. It's really the normalized min cut of the graph. So for instance, for a complete graph, namely fully connected graph, if you do this calculation, every cut is the same really. We cut here. There are n square edges going from here. Each of those edges weight 1 over n, and divided by half of the edges, which is of the order n. And we find that actually the conductance of a complete graph is order 1. And this notation really, this is the capital O notation, which defines the growth property of this rho of t as n goes to infinity. So it's essentially constant as n goes to infinity. And now we use Cheeger's inequality to actually relate this conductance to the spectral gap. We can write the spectral gap in terms of this conductance, or the cuts in the graph. So given that, let's look at some influence in large societies as we take n to infinity. I will consider complete graphs and expanders. Let me not get into expanders because I'm running out of time. But essentially, I look at those are graphs for which the conductance is high. So they are very connected graphs, highly connected. So for such graphs, our bound, and if we have locally forceful agents, namely agents that only influence a constant fraction of agents. It doesn't grow with n. Only a fraction which does not grow with n. In that case, we have that the expected value is close to the 1 over n weighted average. And the intuition is that the more connected the network, the less the effect of locally forceful agents. So this is, I think, one of the main results of this sort of analysis. But let me show you one more graph, which sort of puzzles one when you see it. So it's the barbell graph. So essentially, we're thinking about two complete graphs connected with a line. And let's say one agent influencing two agents in the same cluster. So this is a social network which relates to homophily in society. It's essentially the tendency of everybody to associate with another one who is similar to themselves. So we're thinking about clusters of well-connected societies. Now let's apply our bounds for such social networks. So intuitively, influence should be limited here because the influential agents are on one cluster. Everybody, so this guy is influencing that guy, not somebody from the other side. This is a very well-connected graph. But if we look at the conductance of the barbell graph, where is the minimum cut? Here. And if you do this conductance sort of on this minimum cut, it turns out to be something like 1 over n, implying a small spectral gap. I mean, as a whole graph, this is not a graph that mixes fast. And also a large value of the bound. So that tells us conductance probably is not the right notion. So it's not any cut. It's really cuts associated with the location of forceful and regular agents. So final example, I promise. So one more thing that sort of tells us, because our bounds are only in terms of the total influence, alpha ij, pij, and the mixing properties of the symmetric graph. It really doesn't say anything about how these, the locations, relative locations of the influential agents. So this is an example which tells us we should actually take that into account. Think about 6 agents, and these are the graphs associated with the undirected graphs associated with the symmetric T matrix. Assume that in one of the graphs, the influence happens over the bottleneck, and here it happens over this side. So now, if I don't show you the stationary distributions, which one do you think will be more, which graph will be more or less robust against this information? I think it's showing, but anyway, I'm not gonna, no, I should have used PowerPoint. So essentially, there is a difference here, right? Because here, the influence is being pushed across the bottleneck. The entire right side of the graph is influenced, and the correct information cannot proceed back as fast as it would in this case. So we're expecting that this graph actually is more robust. And actually it shows here, for instance, the 3, 4, 5, 6 has 1 over n type weight. Only the first two are affected, whereas here, these parts are strongly affected. So that tells us we should think about how these relative locations impact our bounds. And that's the last part. So essentially...
Well, I mean, is conductance maybe the right notion if you look at a worst case location of forceful agents?
So conductance is property on the graph.
On the graph, underlying graph.
But so what if you first look at the graph, talk about the conductance, and then let me pick a worst case choice of what forceful agents are going to be?
Yeah, so it's going to be on the bottlenecks, but I'm trying to show sort of given an influence structure, what can I say about, for that particular graph, what's the worst case?
So the question is just, I mean, under worst case location, maybe conductance is exactly the
True.
thing.
That I agree with. I think that may be the case. I haven't looked at that, but that's intuition suggests that. So
5 minutes.
5 minutes, I'm done. So I have two more theorems and we'll be done. So essentially, first thing is to come up with an exact characterization, and we do that by sort of we look at this difference again, and then we can actually relate it in terms of now the mean first passage time from state I to j. And by that, essentially, I mean you start the chain from state I, and then let the chain run, and then what's the expected first passage time to state j? So using, again, Schweitzer's result together with ways of relating fundamental matrix to the mean first passage times, we can show that the influence that node k will have is proportional to the mean first passage time from node I to k. This is the influenced guy, the forceful agent, and this is the forced agent. So essentially, it's how fast information goes to k from the forceful agent and the forced agent. So this, for instance, in the previous example, tells us the sensitivity of these guys, why we still have one here. Because essentially, these are symmetric with respect to their location to the forceful and the forced agent. So then we essentially use this mean first passage time. This is the last theorem. Essentially, what I was mentioning before. It's not every cut that we need to look at, only the cuts that involve the forceful and the forced agent. And here's our final theorem that relates the infinite norm to the minimum cut between subsets which include I and j. So if you go back to the barbell graph, for instance, it's not this cut that we need to care about, but really these cuts that include the two agents on the two different subsets. So that gives us basically a tighter bound in terms of the influence. And the proof essentially of this is starts from the mean passage times, relates the mean passage times to a maximum flow problem, sort of a network optimization problem. We use a very sort of well-known or very strong, powerful theorem in network optimization, max flow mean cut, which states that if you look at a graph, if you pick two nodes and you're interested in how much flow, let's say we have capacity constraints in this graph, what's the maximum amount of flow you can push from node I to node j? And the theorem using linear programming duality states that maximum flow is equal to the minimum cut. And minimum cut, why? Because essentially that's the bottleneck from one side of the network to the other side. So by relating this to such a problem, we can show that it's really these relative cuts that matter in our bounds. So that sort of sums up my talk. Essentially, the goal was a framework for the analysis of spread of misinformation in a society represented by a general social network. We showed that under some minimal set of assumptions, disconnectivity assumptions, misinformation does not prevent convergence to consensus, but this can be to an undesirable set of beliefs. So we've sort of studied bounds on the effect of misinformation and the influence of forceful agents, and showed that if the network is sufficiently connected, and sort of the location of these forceful agents, it also is a matter of location of the agents with respect to the bottlenecks in the graph, then the influence can be limited. So future work is one thing that I'm very interested in, is to come up with bounds on other moments. We only looked at the expected value. So how can we actually analyze variance or second order moments mostly? What happens when the society is not connected? So do we get a limit? That won't be a consensus, right? If we have some agents which only stick to their beliefs, that will not be a consensus across. But it will be interesting to see if we can actually get convergence and try to understand the behavior there. And final thing is, again, here we have influential agents which just stick to their beliefs. What if they're also, in an adversarial manner, try to influence others by sort of changing their beliefs or, trying to manipulate the society? So that's another sort of question that we're interested in. So that concludes my talk. Thank you. Yes.
It seems that the main idea behind the result wouldn't be changed if you changed your definition of forcible agents and regular agents. I mean, all that you really need, maybe I'm wrong here, is it true that all you really need is some sort of asymmetry in the information flow? You have two types of agents, and some of them don't ever learn from others, but they might or may not have influence on someone else. Once you create that asymmetry, then that's going to be
yes. I think if we have pairwise asymmetries, we may be able to use same kind of tools. But here, I have to think about that, because there's special structure in this model, because basically either we do 1/2, or we basically give weights 1, 0. So you're saying if those are different weights, then probably the tools will be applicable, but some of the results may change. The mean passage time coefficients may change. But as long as you're thinking about perturbations, pairwise perturbations, I think these ideas can be used.
So my memory must be wrong, or I'm understanding something wrong. If I think about the voter model on an n-dimensional network, my recollection was that in 2 or maybe 3 dimensions it converges to uniformity, but not necessarily in higher dimensions.
That's a little different, though, water model. This is a continuous model. That's a discrete model.
Okay, because this is a continuous.
Yes, that's a very important difference in the analysis of the dynamics. Exactly.
I was going to ask about that. So at the very beginning of this, you said that it was continuous time and you're drawing agents from Poisson distribution.
Yeah.
I wasn't quite sure what role that played, rather than just...
The only role that played is to make sure the time is continuous. That allowed me to analyze pairwise interactions. Because otherwise, like Golub-Jackson, for instance, has a discrete time model. At each point in time, everybody sort of takes into account the beliefs of all the neighbors.
Well, couldn't you just, like, every period draw someone and then have them interact with someone, and the next period you draw another person?
Yeah, that's also possible.
But would you expect different results
No.
there? So that's just the continuity.
The only thing that will change is this 1/n probably because the way we sort of do this is we aggregate the Poissons, and this gives us a 1/n factor.
In your bounds, so the forcible agents actually were convincing the other person with probably 1 minus epsilon, or right? I mean, is that the right way to say it? The other person was putting that much weight on the forcible person's beliefs. But your bounds, we didn't really see epsilon later in the talk, so it seemed like
It's independent of epsilon. It's
so can you just let epsilon go to 0 and get rid of that?
I think so. The only issue is in the convergence analysis. So in establishing this fact that each term of that matrix is strictly positive over those instances, that's where we use that. But I think if you do a bit messy calculations, you can find positive probability events in which, if you need to consider, I think, longer time instances, you can get rid of that epsilon, I think. But right now, I think it's a technical assumption that allows us to do the convergence analysis a little easier. In the perturbation bounds, it doesn't show up.
But if you push epsilon towards 1, that would sort of should slow down the rate of contagion, right? So that if I'm putting only 5% weight on the forcible agent, and I'm just holding on to my beliefs of 95%, that should perhaps slow down the rate of contagion and therefore affect some of these things.
Yes, it does. I will get tighter bounds.
Okay.
These are assuming
Okay.
upper bounds. Yes, exactly. So that's why it doesn't show up. But I think if the analysis could be tightened to get tighter bounds. Yes.
Can you give me some intuition? Since this is a multiplicative process, why is it that it's the arithmetic mean, W bar, that comes in instead of the geometric mean of those matrices? Do you understand what I'm saying?
So the arithmetic mean, you mean this uniform stationary distribution?
You took W bar to be
Oh, okay. Yeah, I know. So basically, if the reason is here, if you look at the symmetric part of the matrix, what we get is both row stochastic and the column stochastic matrix. So that preserves the average at each instant in time. So the average never gets changed. That's why we converge to the average. For the geometric mean, I don't know.
Okay, I mean, it's not a well-formed question. It just seems to.
But that's a very key property of this doubly stochastic, of multiplying with doubly stochastic matrices. We preserve the average.
Any other questions?
Well, thank you, Lauren.